Unit 5 is going to tie a lot of what we have been doing in previous units together, but now expand on those ideas with exponential functions, logarithmic functions, and inverse trig functions. So if we're going to spend some time working with derivatives and antiderivatives of those different types of functions, it would probably be worthwhile for us to spend a little bit of time reviewing those functions and reviewing the ideas of inverse functions and reminding ourselves, how do we use logarithms and what are they? So that's sort of the purpose of this section here, 5.0, not really a whole section in and of itself, because almost everything in this section you should already be familiar with from Algebra 2 and Pre-Calc. So the first thing that I want to talk about here is an inverse of a function. So two functions, f and g, are inverses if and only if, when you substitute one into the other, or you complete the composition of functions, you simplify that to get x. So if I plug g of x in for x in the f function, I simplify to get x. If I plug f of x into the g function, I simplify and I get x. This means that for every point a, b in f of x, there will be a point that is flipping your x and your y's there in g of x. So if I had the point 2, 0 in f of x, I would have the point 0, 2 in g of x. Something important to notice is that every function has an inverse. All you're doing is switching x and y to get that inverse. However, the inverse is not always a function. Think about a quadratic. You could just switch x and y, and you would still have an inverse. If I had y equals x squared, x equals y squared would be the inverse. But think about what x equals y squared looks like. It's a horizontal parabola. This does not pass the vertical line test. So are these inverses of each other? Absolutely, yes, they are. However, they are not, the inverse is not a function. So every function has an inverse. That inverse is just not necessarily a function. And when it is a function, it has a special name, and that name is called invertible or invertibility. So a function is invertible if its inverse is also a function. So think about a line. A line and its inverse will be invertible because they are both functions. They would both pass the vertical line test. An invertible function must pass two tests: the vertical line test for the function to be a function, and the horizontal line test for its inverse to be a function. So if I'm looking at an original function, this passes the vertical line test, so it's a function. However, it does not pass the horizontal line test, so it's not invertible, or the inverse of this function is not also a function. In order for this to be true, what can't happen is a change of behavior, right? The problem with a parabola is that it goes from decreasing to increasing, which means at some point when I flip that sideways, I'm going to have an issue. So for this to be true, invertible functions cannot have a change in behavior. They cannot have a change in behavior. And when a function does not have a change in behavior, we call it monotonic. So monotonic means it's either always increasing or always decreasing. So let's hit the highlights from this top section. Every function has an inverse. Its inverse is just not always a function. To find the inverse, you're simply switching x and y. Now in Algebra 2, we typically make you then solve for y after you switch the variables. But know that as soon as you switch the variables, you have created the inverse, right? Then you're just isolating y on occasion, which is what puts it in a form easier to analyze. But as soon as you switch x and y, you have set up the inverse. The second thing is, if a function and its inverse are both functions, then we call that invertible. And that is only true when we have a monotonic function, meaning a function that is either always increasing or always decreasing. So let's look at some examples. So example given that f of x is x to the third plus 5. Determine the equation of the inverse f prime of x. So this notation is telling you that you are going to have to solve for y because it wants you to use function notation. So go ahead and pause the video and work out this inverse. So I'm going to think about x equals y to the third plus 5. So x minus 5 to the power of 1/3 equals y. So I could say that f inverse, and be careful when you're writing this, make sure it doesn't look like a derivative sign, f inverse of x is equal to x minus 5 to the power of 1/3. why don't you go ahead and practice the same process on 1, 2, and 3 below. Pause the video and then unpause it and watch me work through these solutions as well. So on number 1, if I rewrote that and switched the variables, x equals 3y minus 5 quantity to the power of 1/2. So x squared, then I would add 5, then I would divide by 3. I'm doing a lot of the algebra in my head here. This would give me the inverse of f. X squared plus 5 over 3. For number 2, x equals 5y minus 3 quantity to the 5th power. So x to the 1/5 power plus 3 divided by 5, just isolating y, is going to give me f inverse, not f inverse, g inverse of x. And number 3, x equals 1/2 y to the power of 3 over 5. So 2 times x, and this whole thing is going to be put to the power of 5/3. It's going to equal, not f, h inverse of x. So for inverses, switch your x and your y, solve for y if they specifically tell you to, or if you're being asked to write it using function notation to find that inverse. We're going to be talking about inverses a lot in 5.3. For the next problem, it says, let f be a function with an inverse, f to the power of -1, or f inverse. For part A, given those two ordered pairs, what is the average rate of change from 2 to 5? Well, that just means to find the slope of the inverse. So let's find the slope of those 2 points for part A. So that's just using the slope formula. You're going to get -17 over 3 is your average rate of change. For part B, what 2 corresponding points would be in the inverse? So for part B, the first thing we're going to do is flip the points. Now I have 6, 2, and now I have -11, 5. And then if I found the average rate of change using the exact same method, I would get the reciprocal of that. -3 over 17 would be the average rate of change here. And then part C is saying, what relationship do we notice? These are the slopes are reciprocals, which should make sense since all we're doing is switching our x and our y. Let's look at some more examples. Number 5, since inverses are just switching our x and our y, what symmetry relationship between the graph of a function and its inverse exists? So these functions are symmetric over the line y equals x, since that is what we're doing. We're switching x and y. What about the slope of the function and its inverse? We just said that they are reciprocals of each other. So delta y over delta x would go to delta x over delta y. For inverses, they are reciprocals. Number 6, if y equals the square root of x, what is the inverse? Just switch x and y, don't actually solve, so the inverse would just be x equals the square root of y. For the second part, it says find dy dx of both equations. Note that you will need to use implicit for the inverse. So go ahead, pause the video, take the derivative of both the original y equals the square root of x and the inverse x equals the square root of y. So for the original function, we're just going to get 1/2 x to the -1/2 power. When we take the derivative with respect to x of the inverse, we're going to get 1 equals 1/2 times y to the power of -1/2 times dy dx. So if we're going to isolate dy dx, we would get that dy dx is going to equal 2y to the power of +1/2. What do you notice about these derivatives? These derivatives are not reciprocals of each other. They definitely look like they have some sort of close relationship. They're similar, but they are not exactly reciprocals of each other. And again, that's something to keep in mind when we get into 5.3. The very last thing I just want to briefly review before we get into this unit there's some properties of exponents written in here. You should know how to work with properties of exponents. You should know how to work with negative exponents. We have been working with many of these rules along the way. But the key thing that I also want to remind you about is logarithms. We have not worked with logarithms yet. So a couple of things to know. A log and an exponential function are inverses of each other because a log is an exponent. It's asking you what exponent makes this statement true. And also, if you think about an exponential function or a logarithmic function, it is always increasing or always decreasing. So it is monotonic, which means that logs are invertible or exponentials are invertible. Now, this whole section right here of properties, how to expand and condense logarithms, really just that part right there. This is going to be huge for your ability to manipulate problems in this unit. You have to know your properties of logs. You have to be able to look at something, and most of the time you're going to be expanding, because expanding with logarithms means that we're creating more terms, polynomial-like, and it's much easier to integrate or differentiate when we don't have as complicated of a function. So it's really important for you to be practicing and to know how to manipulate with logarithms. Also, and we will talk about this more in the next section, we only work with the natural log function when we are in calculus. So regular log, the log log, is used in many other classes. It has a base of 10. There's reasons that it has existed to fulfill a purpose. However, in calculus, the only logarithm you're going to be working with is natural log. So if you end up seeing a problem that has a different type of log, we're going to immediately use the change of base formula to convert it to be a natural log. So quickly pause this video, work through expanding on A, B, and C, and then unpause the video and see how you did. So for part A, when we are expanding, this becomes natural log of 5 plus 2 natural log of x. On B, when we're expanding, this becomes natural log of 3 plus 5 natural log of x plus 1/2 natural log of x plus 1. And then part C is going to get a little bit messy, but I'm going to try and fit it in here. It's going to be, let's use a different color so it doesn't get too smashed, 1/2 times the natural log of, and I'm going to just take that 1/2 out and leave the rest. Actually, let's do 1/2 times natural log of the numerator x squared plus x to the 5th plus x squared minus x, minus that denominator, natural log x natural log of e plus 4 natural log of x. You could take this one step further and simplify this, since natural log of e, x natural log of e is just going to be x. But I'm just going to leave it like that for now. So you should be very, very comfortable expanding logarithms. One last thing I want to remind you about, and we're going to use this sort of proof we're going to use in future sections. So I want to remind you about the change of base formula. And how this works is if I have something like x equals b to the y, I could rewrite this as natural log of x equals y times natural log of b, if I am simply taking the natural log of both sides, which means that y is equal to the natural log of x over the natural log of b, if I just solved for y in that particular problem. Thinking about that in terms of the inverse, if instead I had y equals b to the power of x instead of x equals b to the power of y, again, the first thing I would do is natural log both sides. So I would have natural log of y equals x times the natural log of b. Then I could put both, I could raise e to the power of both sides. So e to the power of the natural log of y equals e to the x natural log. Whoops, this b right here should have, or that y should have been a b. So this should be e to the x natural log of b. And then e to the natural log of y is just y. So y equals e to the x natural log of b. So these are the change of base formulas that we're going to be using in future sections in order to manage and deal with logarithms. So I wanted you to see the proofs for them here. We will revisit these a little bit when we talk about integrating and differentiating with logs and exponential functions. Look forward to seeing you in class. Thanks for listening.